Hello, everyone. Well, it's a pleasure to be here. I'm learning a lot. My primary background is machine learning, and I think a lot about things that fly and communicate. So today, I'm going to talk about some of the aerial platforms with which we do perception action loops. So, I heard the previous speaker, and after speaking to several of you, you were thinking about next gen, 6G, and these are pervasive sensing networks, and they communicate, and you're looking at, machine intelligence networks. So I'm going to give you examples of, at least two different networks that already exist, which are sensing, pervasively. And I think there are a lot of lessons we can learn from them. So, let me just introduce some of my work. So, I run an autonomous systems research team that is primarily focusing on aerial robotics. We work in all different scales. We have tiny robots, we have medium scale robots, we have real aircrafts, and we have a network of, weather balloons, commercial aircraft, satellites, etc., right? And this is an arrow just showing the difference in altitude. One thing that is common across all these platforms is that there are a few components. One is you need power. You need to power up your electronics, right? That's battery. And interestingly, for most of the small form factors, the density of weight, the weight is actually most of it is battery, right? And of course, it gets better as you go towards the bigger form factors. But again, when you're coming to weather balloons and microsats, that's again is a challenge. So bulk of your weight, payload is power, and so that limits your ability to sense, process, and communicate, right? So the second thing is, of course, sensing. There is a lot of commonality across many of these platforms. So for instance, we are looking at IMUs, we are looking at GPS sensing, cameras, radar, LiDAR, depending upon the form factors. So again, there is some kind of a standardization, at least in my research area, that's happening there. Processing, again, as I said, the primary use case for us is machine learning, and depending upon how things are moving along, I think there is a standardization, and again, I would say that there is ways to go. The way we are making progress in machine learning is requiring us to rethink how we are building hardware. And that has a ripple effect. Again, if you're using something like a Crazy Fly, which is a tiny quad rotor, I don't have any processing to run any kind of current machine learning system on board. It has to be on the cloud. It has to be at a server I need to communicate. Whereas if it's on, for instance, a big aircraft, probably you can carry an NVIDIA GPU, and maybe few of them, in fact, right? The actuation, pretty much, again, standard, most of them are motors, depending upon the form factors. These are large motors or small motors. Sometimes they are powered by gas, sometimes they are powered by electricity, right? And of course, communication. And this is the interesting one. For the large form factors, they have a big payload. So communication, sure, you can carry a lot of payload, but the problem is, connectivity. Whereas as you go on the low side of the spectrum, you can't carry a lot of payload. Sure, the connectivity is there. So there is an interesting trade-off, and I'm going to talk a little bit about it. So again, to just give you a sense, right? Those are some of the real-world things that we're dealing with. I am a field roboticist, so we are building these and deploying them in the real world. So we are trying to do a lot of workarounds, and I hope some of this thing will influence on how you guys are thinking about the next generation of communication networks. All right. So one thing that I'd like to emphasize, if one thing that you want to take away from this presentation is that autonomous system and robotics is getting overhauled. I mean, this autonomous systems in 2020s is very different than how we did it 10 years ago, 15 years ago. And that's happening because of a couple of reasons. So first thing is deep machine learning is basically, upending a lot of things. The way we train, deploy, do inference for machine learning tasks is vastly different. And any roboticist, you talk to them, that there is AI or machine learning component that's going to be in the pipeline. I mean, you've got to reason about the environment that you're operating on. So there is no workaround. So machine learning will be critical, and it's moving towards deep machine learning. And second thing is cloud computing, right? A lot of these machine learning workloads are happening on the cloud, right? So interestingly, if you look at 10, 15 years down the line, I have a lot of students from CME Robotics Institute, and they think very classically for robotics. So they have these planners and these controllers and these perception system, which are boxes that have been individually trained, sometimes using classical code. But slowly you are seeing, at least in the perception system, that they are rapidly moving towards deep neural networks. And these are huge, big neural networks, right? And, and many of these times we cannot run these perception models online on the edge, right? In some cases you can, but in many of the small cases that I am interested in, we cannot. Right, so it's upending the whole, the way we build robots. And this is also percolating down to, the sphere of cyber physical systems, right, where you are perceiving and you are taking an action, right? So this is something I think, will be very useful for a lot of you as you think about the next generation technologies. So here are a few of the expectations as a field robotist that I'm going to, make, right, that what I expect for me as a field roboticist to make things work in 2030. And again, this is my perspective. I'm going to support it with few of the research works that we have done in the past. But again, I'm happy to debate and argue. And this is, again, as I said, is a speculation, but hopefully informed speculation from our work, right? So first expectation is that pre-training and large neural networks will be central, right, to many of the applications that you call pervasive sensing. And the reason that I say so is we have to look at the history. So if you look at some of the recent advances in, for instance, computer vision and natural language, they have moved towards this model of what they call pre-training, where the idea is that you have these pre-trained networks, large neural networks that are trained using self-supervised techniques. So you might have heard of GPT-3 and BERT and all those things, right? In computer vision, that has also happened, and more recently, also in the multimodal computer vision space. So, this has significantly changed how NLP happens, how computer vision happens. And our hypothesis, again, is that this is going to change how robotics and reasoning in cyber physical system is happening as well. This is, I wouldn't say this is established fact in robotics, but I am from the camp that we believe that we are going to see this kind of shift, right? So what it means that, if in classical robotics, you went and built these planners and controllers and you put them together, I think we are going to start moving towards these pre-trained deep neural network fabric that does perception and action loop. And you can actually fine-tune for many of these tasks. Already we are seeing some of these, proof points. So for instance, we have, I'm referring a few of these papers where you are actually, pre-training a network and then you're fine-tuning for some of these end effector tasks that you might be interested in. And of course, there is a lot of advances in general representation learning that's very useful in here. From our own lab, we've been thinking about pre-training just for autonomous systems. So what it means is that imagine if you have a robot that has a bunch of sensors, many different kinds of sensors, including cameras, LiDARs, IMU, depth, GPS, whatever it is, right? And in the end, you want to solve various tasks in your robotic stack or in your cyber physical system perception action loop, for instance, right? For instance, you might want to figure out the localization or you want to control things. You want to identify if there is an obstacle or not. You want to plan on all those things. We have some initial models that validate this hypothesis that it's possible to actually create these pre-trained fabric over which you can do fine-tuning for various robotics tasks. So again, I won't get into the technical details of it. I'm happy to refer to a technical report that does that. But for instance, what can we do with it, right? So what we can do is we can definitely do perception. So for instance, we have done deep control policies both for aerial vehicles as well as cars using these pre-trained fabric. We talked about mixed reality in the previous talk, for instance. Like these kinds of models can actually help you create some of these simulation models or do inferences in simulation models. So a simulation is, again, it's basically a collection of bits that allows you to mimic reality. So it's possible to actually channelize all this information that you've gained in this pre-trained fabric to create simulations which mimic reality. And of course, the great thing is that if you have a fabric like that, it gives you technically a path to integrate some of the big learnings that are happening in natural language. So there is a lot of value in thinking about such deep neural networks. Again, proof points, things like visual odometry, which is our ability to figure out where a robot is using just an images of camera, images from a camera, is central to many robotics, be it classical or be it deep, end-to-end learning-based camp. You can do that. You can do it with such pre-trained fabric. Again, I won't go into the details. Happy to give you the numbers. Things like drone navigation. Where you are taking an image, from an image you're trying to figure out what the right control is, right? Where should you go? You can actually do that with pre-trained networks. Same thing with different form factors, not just for aerial. You can actually use the same form factor because it encapsulates the knowledge of how the visual perception moves as you move around in the world. This is all feasible, right? So the thing is, if you believe that this is how the robotics will be done in 10 years, right? It has deep implications. So the first thing is that these are huge models, right? Even like, for instance, if you drive a Tesla, probably you're following how the autopilot is being developed. It's a collection of deep neural networks. Sure, you have a car that can carry a big bulky computer, but if you're flying form factor, we don't have that luxury. So a bulk of that computation needs to happen on the cloud. So what it means that I need to send data up to the cloud. And what kind of data I'm sending up the cloud? This is a high bandwidth, high information bandwidth data, often LiDAR images, RGB images. Maybe I could do some kind of encoding and then send it up to the cloud, but still I have to send a lot of data up there. And then I have to get a control command back. And again, there are some interesting things with that, right? So first thing that I talked about was deep ML. The second thing is real-time control over networks will be crucial. It's extremely crucial for the application that I am looking at. And I'll give you a few examples why, the current paradigm of reasoning in the cloud and sending the control commands back to us kind of is suboptimal, right? So if any of you have played with OpenAI Gym and reinforcement learning techniques, right? So this is basically probably familiar to you. What this is an agent. It's a bipedal robot that you're trying to basically control using reinforcement learning. And what I'm showing you is exactly the same underlying algorithmic framework. Nothing has changed except the frame rate. One of them is at 20 frames per second, another one is at 1,000 frames per second. And for one case, we can actually learn this thing really well. And for the other case, we don't make any progress at all. And nothing has changed, right? The only thing that has changed is the frame rate, right? So, one of the, big criticism that I will make for the machine learning community is that we don't think about time as formally as we think about everything else, right? So if you're doing reinforcement learning, you have some frames coming at it and you have some delta t and that's thrown on the rug. And what happens is that you have these policies which are extremely fragile to the delta t, the frame rate, right? So, but as a field roboticist, we got to deal with it, right? So for instance, this is the drone racing drone that we had created. And in this case, one thing that we realize is that even when everything is on board, the frame latency is actually, quite high. So for instance, the image feed rate from a camera is usually 30 hertz, but because of various overheads, computation overheads, that changes. Just between 30 hertz plus minus 5 hertz, our policy that we've trained using some of the most sophisticated machine learning techniques actually fail, and we have to account for that. Right? So in this case, we came up with a simple heuristics that deal with it, but it reduces our frame rate to 10 hertz, even though our camera is capable of 30 hertz. Now imagine, this is why when the computation actually is happening on board, imagine when I'm sending all this data to the cloud and it's coming back to me. I mean, it's going to hurt quite a bit at that time, right? And we have various experiments that show that higher frame rate actually makes your machine learning problem much easier, right? So having some kind of quality of service, not only on latency, but also on the jitter of the network will be very crucial. And that's something I don't think is voiced enough from machine learning community. But as someone who's doing field roboticist, field robotics, I would love to learn more and see how we can build upon your expertise. So the third thing is the data. Right? So I talked about machine learning fabric. We talk about real-time control. The third thing is all these large machine learning models, you need extreme amount of data. The great thing is that, with the promise of 6G, where we will be hopefully, collecting all this data, we should be able to, solve some of the challenges. So let's, let me just move past this. So let me just give you a very simple use case. So this is an existing network of airplanes that exist out in the world. So what I'm showing you is that imagine you have a wind field and you want to go from a start to end on an airplane. So what you got to do is you got to know what the wind field is. If you know what this wind field is, you can actually, really cut down on your flight time. So, I grew up in India and I often go to India and it's 16-hour flight time. Sometimes that flight time reduces to 12, 13 hours because when you can have, favorable winds. And in fact, there are teams in aviation circles that are trying to optimize this thing, but they are trying to do it with very sparse amount of data. So this is a pervasive sensing network that already exists, right? Right now, if you go to flightaware.com, right, you'll see probably 20,000 airplanes all over the world. And the great thing is that we have created infrastructure. So for instance, there is something called FAA ASD feed, where you can query the status for each of these aircraft right there. Right? Sure, it's a network. It's a, it's a network with high latency. In that case, all the data is coming after 5 minutes of delay. But this data exists, and we've been able to, harness information from this, from this network to build very sophisticated weather maps. But there are few lessons that I'd like to point out that we can learn from it, right? So the first thing is you can imagine, right, all right, if I want to have wind information, right, if you do a simple vector algebra where, you know where the airplane is heading and you know what the ground speed is, you can basically do simple, high school vector algebra and figure out what the wind velocity is. Unfortunately, this network is designed such that we have incomplete information. And, as a computer scientist, as someone who's interested in weather, I am bewildered by some of the choices that have gone into into this network. Sure, the primary purpose of this network was air traffic monitoring, but it would have required only few bits of extra information for us to actually, get real-time weather feed. And the interesting thing is in 2020, the ADS-B mandate rolled out, which is the next gen, communication from these aircrafts to the ground stations, and even that, some of these things were not fixed, right? I've had chats with folks at NASA, for instance, and some of the folks at FAA, and I couldn't find a single authority who could tell me why we couldn't spare few more bits to carry some additional information, right? And the reasons I've heard is from lack of bandwidth to regulations and things like those. So again, our ability to be flexible, ability to ingest data, our ability to demand some of these newer data for the near use cases will be very important. I don't know how would you implement that at the levels that you guys are working on, but that's something to think about. The second thing is privacy. All this data is coming out in clear text, and that's one of the mind-boggling things. Again, as someone working in computer science and thinking about security, right? All this data is available for anyone for free, and it's been broadcasted in clear text. You can actually put your software-defined radio tuned to it, and you can actually see everything right there. In fact, there are some apps. I'm sure you take your cell phone app, and if you have a plane, you just point it out to that, and it'll give you all the data out there. Again, for this application, maybe not a big deal, but when we think about other AI use cases, The issues of privacy will be, will be important. The issues of data provenance, if I have some of my data and I'm broadcasting it and I'm giving it away for free, I think, there are some questions around it. There are issues of federated learning. Again, I'm not an expert in those, but just highlighting some of the things. I know this is, I think, the last thing actually. This is expectation number 4, so that's a typo. Coverage on steroids. So other pervasive sensing network that we work with is the network of weather balloons. So right now, all the weather information that we get from stratosphere, right, which is basically 60,000 feet to 130,000 feet, is mostly coming from remote sensing. And that's an extremely important band for various reasons, because that's where the jet streams are. That's what changes our macro level weather at a, it's a very important band that we are completely missing. So what we have this network of weather balloon, which is almost 100 years old. We've been flying these weather balloons for 100 years. So what it is, this is basically these balloons. So at around 200 sites across the world, 200 sites in US and more than 1,000 sites across the world, they do these balloon launches. So in the morning and usually in the evening. And what it is, these are weather measurement devices, sensing devices that you release. They'll go up to 110, 120, 130,000 feet. And then basically, you collect it. Sometimes you're able to collect it, sometimes you're not, right? But this is a sensing network that's 100 years old, and we have very primitive means of collecting the data from it, right? So we've been thinking about how to make it better, and one of the ideas was that you can actually think about biodegradable sensors, which you can, release as contrails, right? And again, this is work with some of the folks at CMU. And we've been thinking about various actuation strategies so that we can recover these things much more quickly. They are more efficient, provide more dense things. But interesting thing with these devices is that they are really tiny. Lifetime is less than 3 hours. The kind of payload they have, I mean, it's negligible. We cannot afford to carry a lot of payload here. So, in the interest of time, I'll just quickly, show you how you communicate. So as a field roboticist, if one thing that I could, I wish I had was a better communication, paradigm for these kinds of devices. Right now, it's so complex. What we do is when we drop these tiny sensors, we basically send through LoRa the data to the weather balloon that's still ascending. And that weather balloon communicates via the Iridium satellite, which then relays to the ground. And, I would say that 50% of our engineering went into that instead of, the other things that we want to do. So our ability to, again, communicate with these devices which are small and which are spread globally is very important. And I do, find myself limited with that. All right, so I'm, a couple of minutes from my timeline, but 4 things as a machine learning practitioner, field roboticist, that I wish to see in 2030. So first is, of course, supporting edge and cloud compute. I know that I'll be doing pre-training, and that's all, we are throwing all our eggs in one basket, which I am a strong believer in. And of course, this is, we can debate about it. We got to think about latency and jitter, both from algorithmic point of view, but also, from maybe communicating with this community and figuring out, what are the quality of service requirements there. Data transmission, provenance, security, and privacy is important. Again, there are various folks in machine learning community that think about it. I'm not the primary expert, but I do know that these are important considerations. And finally, network coverage. One example I gave you was weather balloon. The other example is we did, DARPA sub-T challenge with folks at CMU. And here the challenge was that you have this robot or a team of robots that's going into a cave. Again, you need to maintain communications that they're going into a cave and they're doing everything autonomously. So the hack that we came up with was that every 100 feet, they would just physically drop a Wi-Fi router. And that was our communication. Again, as I said, a lot of engineering went into it. And I wish there were easier way to communicate with these devices. So with that, I'll conclude. Thank you.